Morning. All right, here. Good. Alrighty, so we're going to get started today. Does anyone want me to go over the solution of the homework assignment? Or do you guys think, you pretty much have it already?
It's in the past.
In the past. Okay, maybe I can move it to the lab time. If anyone wants me to kind of show you how to get to the solution of the homework assignment, we can talk about it during lab time. Yep.
Well, the only issue I had is like when I tried to make the tarball, it just wouldn't do it.
It wouldn't do it.
Yeah, like it kept on saying PWD directory does not exist.
It has to be back quote PWD. The back quote.
Oh, the back.
It's there's a backtick, which is the upper left-hand side of your keyboard. It's the tilde key.
Oh,
but without shifting it.
That's part of the problem. I was using the single quote one instead of the back quote.
Right, because that's why I changed the font in the command here, so it is show up as a backtick. So you kind of have to do that part carefully. Yep. Alrighty. Well, since we are on it, might as well talk about the new homework assignment. So this time we are not looking for eggs, we are looking for bunnies. Yeah, so we are hunting bunnies instead.
That's really left?
Well, the Brits do that a lot. I mean, the British people actually hunt bunnies using air guns. All right, so this is an interesting homework assignment, so I'll go ahead and describe what you have to do for this homework assignment, and then we'll go back and talk about the concepts of what you need to know in order to get this done. Just like with the other homework assignment, you start with a tar.gz file, which will decompress into a folder. So we'll go ahead and check it out. All right. So tar xzbf downloads. This is called Bunny Hunter. Bunny Hunter. All right. So the file is called more bunny. Okay, it should be more bunnies instead of more money. But it's not formatted nicely because it is a little bit wider than what the terminal has. So let me see if I can, maybe if I get rid of line numbers, it's a little bit better. Okay, there we go. So the instruction is already here. The first thing you might notice is instead of starting with .text, this one starts with .data, which means we are starting with the data section where content can be changed. Okay? If I start with .text, that section is only intended for instructions that the program executes, and content is not supposed to be changed. This time, we start with .data, where it can be changed. We do L1 colon, which is the definition of a label, just like with your previous homework assignment, and then a .fill 256. The .fill directive is a directive, which means it is instruction to the assembler. It does not actually translate into actual instructions in the output code. So what it tells the assembler to do is to reserve 256 bytes in this case, and initialize all 256 bytes into zeros. Okay? So we are allocating 256 bytes in the data section where I can make changes later on. Then I switch back into the .text section here so that you can specify your code. We have the typical .global start, which is basically exporting the label _start so that the linker knows where's the entry point of your entire program. The label _start kind of serves the purpose of your main subroutine or the main function in a C program. And then we define the label _start, all the label definitions, and with a colon. Okay, so that's how you can tell that this is a definition of a label. And this time, this is what you need to do. Write any code necessary between the labels _start and check here, which is all the way down here. You can write any assembly code as long as, one, you do not change the bytes in the .data section, and you do not make any calls to any subroutines, any functions. Because I know some of you are going like, hey, I can call this blah, blah, blah function and do the same thing. So I'm making you guys actually do the hard work and write all the code in assembly. So by the time you get to check here, at this point, EAX should point to the memory location of 5 bytes. In order of the address would be 62, 75, 75, 6E, and 79 in hexadecimal. Okay, so you want to look for those 5 bytes. To test this program, I will, that's me, will initialize the 256 bytes starting at label L1 with test cases. So I will basically load it up with special test cases. And then I'll go ahead and run your code, stop at the label checkpoint, check here, and see if the address that I'm expecting is in EAX or not. Okay, so that's how I'm going to test your program. Note that this program has sufficient complexity that most implementations should be slightly different from one another. There are many, many ways to do it, okay? And I do not need the most optimal way to do it. So don't try to spend your time to optimize the program. Just get it to work, okay? I can tell whether a program is artificially altered just to look different. So please work on your own program and do not share any code. So when you're working on this program, you can work in the group when you're working on homework assignments, but do not share any code when you are working together. Okay? Are there any questions? Go ahead.
I'm kind of missing what you want us to do. I don't quite understand that.
Okay, so what I'll do in today's class is I will give you some demonstrations. You are looking for 5 bytes. Okay, five consecutive bytes, and the consecutive bytes would be 62, 75, 75, 6E, and 79 in hexadecimal. So you're looking for those 5 bytes within the 256 bytes in starting at label L1. Okay.
We're looking for those values.
You're looking for those particular values. So what I will do is I will teach you guys how to load up a test case. Okay, how to load up, into L1, a particular test case, so they can run your code and test how well it is working.
These are all going to be continuous, or like somewhere within 256, and they will be continuous, or they're all going to be separate?
The 256 bytes starting at L1 is contiguous.
Yeah. I mean, the ones that we're looking for, are they together or are they all spread
They are
out?
together.
Okay.
So 62, 75, 75, FE 79 is exactly the sequence that you're looking for. And by the way, those are the ASCII code of B, U, N, and Y. Yes, so we're looking for a bunny within range. All right. So what we need to do today is to go over a few instructions that you will need to know to get this homework assignment done. If you go back to the description of the homework assignment, it also describes here, right here. If the pattern is not found, the code should reach check here also, but this time with 0x, basically all zeros in EBX to indicate the pattern is not found. So you have to basically terminate whatever code that you're writing when the pattern cannot be found. Is that okay? But what you're looking for can be hard coded. Okay, it's just B, U, N, and Y, in hexadecimal as bytes. Okay, I'm not going to change the pattern that you'll be looking for. I'm just going to change what is initialized starting at L1. All right? Yep.
It needs to be that complete pattern, correct? So if we find the first, say, 3 values,
It
the
doesn't
rest
count.
Right, doesn't
Correct.
count. Okay, so
Yeah, it has to be the 5, all 5 letters.
okay.
Yep, all 5 bytes. Yep. All right, so this one will take some time, okay? My recommendation is to get started early, okay? So when we have time on Thursday, you can bring your questions to class and say, well, I'm here, but I'm not quite sure what to do next, okay? Or I have questions about this particular instruction and stuff like that. All right? Yep.
EBX is 32-bit long, right?
Yes, EBX is 32-bit wide.
And 5 bytes is 40 bits.
Exactly. So with one single compare long, you can find out the 4 bytes, and then you need one more to confirm that 1 extra byte. Or you can do something else to do the same thing. So, there are a few ways to do it. And that's why I'm not expecting any two programs to look the same. Okay, they might be structured in a similar way, but they cannot possibly be the same, okay, because there are so many ways to get this done.
Do we have to have the specific value in EBS? Do we have to, can we put it, because we have
Say again?
because we have 5 bytes, the
No,
value there.
EBX is supposed to be an address. It's not, the pattern is not in EBX. EBX is a pointer that points to the memory location of the first of those 5 bytes.
Oh, first.
If those 5 bytes can be found.
Can we find it?
Okay. All right. So what we'll do is we'll start to talk about a few new instructions that you will need to know. In order to get this done. Okay. So we'll start with the add instruction. Very exciting instructions. Actually, we did talk about the add instruction last time. Okay, so we'll start with something else. We'll start with the compare instruction, which is the same thing as a subtraction, except.
We look at the sign of it? No.
No. The compare instruction is the same as subtracting, except what? Okay, with a subtraction instruction, you store the difference. With a compare instruction, you do not store the difference. Okay, so we'll start with that. Okay, we'll start with the subtraction instruction here. And I'm just writing a real simple program here to illustrate the subtract instruction. So I will move a particular number, like 45, into a register, let's say EAX here, and I'll do a subtract long. Now the subtraction instruction, just like with the move instruction, the first operand is a read-only operand, and then the second operand is a read-write operand. Okay, so that means what we're doing is we're subtracting the first operand from the second, and then store the difference in the second. All right. So in this case, I can specify a subtraction, kind of like this one. Okay, I'm subtracting -4 from EAX, but EAX already has a value of 45. So that means I should end up with 49 in EAX after these two instructions. Are there any questions about? Yep, go ahead.
So you said it's a 49 after subtract 4.
After subtract long, because I'm subtracting -4, so it's double negation. It ends up adding 4. Is that okay? All right. And that's the entire program. So I'll just put a no up here so I have a place to stop, after this is all done. Okay? And we'll go ahead and assemble the program. Sub.o, sub.s. And then we'll go ahead and just run the program, list it here. Okay, let me move it a little bit so it's not confusing. There we go. We'll put a breakpoint on line 7. There's no point in executing the program past line 7. We'll put a breakpoint on line 4. Run the program. Now we are ready to execute the first instruction, which is a move long immediate 45 into EAX. Without the $sign, it is a direct operand, which is not what we want to do, because location 45 is not somewhere that I have access to. Okay, so this is a move immediate, which means the expression 45 specifies the value that I'm actually copying into EAX. It is not specifying an address at which I copy a few bytes. Okay. All right. Single step. Print $EAX. It is 45. No big surprises here, right? Execute a second instruction, which is the subtract long instruction here, and print EAX. No surprises here. It is just 49. But I'm kind of interested in the flags. Remember, whenever you perform addition, it affects the 4 flags that we have talked about. Whenever you perform subtraction, it will also affect the 4 flags that we have talked about. What do you think would be the Z flag?
0.
The 0 is off because the result is non-zero. What about the sign flag? It would be off because the result is not negative. What about the carry flag?
0.
It'll be a 0 because there's no borrow. Okay.
Subtraction.
It is a subtraction. Okay, so we'll kind of think about this a little bit. Okay. When we talk about the sign flag, we're definitely looking at the number from the signed perspective. When you're looking at the borrow flag, it is not signed. You have to look at it from the unsigned perspective. Okay. What is the bit pattern representing -4?
-4 is 1, 1 is 0 back.
And let's see here. FFFF is -1.
So you would have to,
so you have to go
30,
back.
So you need a 0.
FC would be a -4. That's a lot of ones, right? And the other number is only 45. 45 is, only taking up, 2 hexadecimal digits. So the borrow flag actually should be set. Okay, so we should see the carry flag being a 1. The last flag is the overflow flag, which is basically saying from the signed perspective, the sign of the result does not make sense. Is the sign of this result making any sense? Yeah, it's fine. Okay, so that means we should only expect out of the 4 flags, only the carry flag should be set. The other 3 should be off. Well, let's double check. IR, E flags, and you can see the carry flag is on. All the other flags are off. The IF, and is not useful. PF and IF are not of any importance to us in this class. All right, so that's all good.
Is that 203 means and? How can we? That value didn't show it's a 1 or 0.
Well, the E flags itself is a 32-bit register, and it does have the bit pattern of, the equivalence of 203 in hexadecimal. But we don't really need to know that. We just need to look at the flags and see which one is on and which one is off.
If it's off, it's 0.
Huh?
The value flag is 0.
If you don't see a flag within the square brackets, it is off. That's what we talked about last time. All right. So are there any questions about this particular program? No questions? Okay. All right. So next thing is to talk about the operands. What do you think I can use as the first operand and the second operand? Just about anything. Okay, the first operand can be anything, can be immediate, can be register, can be indirect, can be direct. Okay, so it can be all four addressing modes that we have talked about so far. The second operand, being the destination, cannot be immediate, because immediate is kind of like saying const. Okay, in C and C++, and it doesn't make sense to store something into a const variable. So that's why the first operand can be anything. The second operand can only be the other 3. Cannot be a immediate operand. Cannot start with a $sign. There's one other restriction. You cannot compare 2 things that are both in memory. So you cannot specify indirect and indirect as the first and the second operand. Only up to 1 operand can be a memory operand. So you can have one as a register, one as an indirect. That's okay. You can have one as an immediate and the other one being direct. That's okay too. But you cannot have one being direct and the other one being indirect, because both a direct operand and an indirect operand they're both memory operands. They both need to refer to memory, and that cannot happen. It's just a limitation of the instruction set that you cannot support both operands being memory based. All right. So just to illustrate what I mean by that, okay? So I cannot do something like underscore start here and indirect here. That cannot work. Not that this code actually makes any sense, but but in terms of operands, this is a combination that cannot work. Yep.
Is that true for all arithmetic operators?
It is true for all instructions, all opcode. So move has that restriction, add has that restriction, subtract has that restriction, and compare has that restriction as well. Yep. So basically all instructions that require 2 operands they all have that restriction. So what we'll do is we'll just go ahead and reassemble this program and see how the assembler is going to complain about this. Okay? So we go back to the assembler, and it says, line 5, we have too many memory references for the subtract instruction. Okay? Because you can only have up to one operand accessing memory. Yep.
Is it like a security risk? I mean, security.
No, it's not because of that. It has to do with the architecture of the processor itself. The memory pathway is there's only one path to memory, and you can only use it on one of the operands. So that's why it cannot support two. So even though it's a cis architecture, it still has certain limitations that is inherent to the core part of the processor. Yep. All right. So any other questions about the program that we were looking at? This one here. All right. So let's change this code a little bit. Okay. So I'm going to put it back to what it was. And instead of subtraction, I now specify compare. Okay. So in place of the subtract instruction, I have the compare instruction. So what this would do is it will perform the subtraction just like before, except the result is not stored. That's all. That's the only difference between a subtract long instruction and a compare long instruction. Right? So are we good on the compare instruction? It's essentially the same as a subtract instruction. It is subtracting the first operand from the second, but it does not store the result.
What is that value? So then what does the value go?
We just check
no
the flag,
flag.
right?
Yep, it is just comparing.
Oh, okay, so after we've done that, the flags will be set.
It will change the flags just like a subtract instruction, but it does not store the difference.
Oh, so we get to keep our registers the same.
Exactly. So in this case, after the compare instruction, EAX gets to keep its old value of 45, but the flags will still be changed exactly the same way as the previous program. All the flags except for the carry flag should be clear. Okay? So that's the quickest and easiest way to understand the compare instruction, is it really is just a subtraction with one little difference. Okay? All right. So we have talked about the move instruction, which is nothing more than a copy instruction. Okay? Give me the first operand, I will copy it to the second operand. In other words, if you want to quote-unquote equate this to C and C++ concept, the second operand is the left-hand side of an assignment operation, and then the first operand is the right-hand side of an assignment operation. One specifies the source, the other one specifies the destination. Right? Are there any questions about the move or copy instruction? We talked about the add instruction last time, and today we talked about the subtract instruction and also the compare instruction. And also the very important restriction of you can only have up to one operand accessing memory. You cannot have both of them accessing memory. So are there any questions related to these group of instructions? Well, obviously, if you are to write a program, to do what I want you to do, these 4 instructions by themselves are not sufficient. What are we lacking? We don't have a way to make a decision and go, hey, sometimes I want to go that way. I want to continue execution, not with the following instruction, but I want to specify, hey, I want to continue execution over there or over here. Okay? So let's talk about those instructions. Those are called jump instructions. And let me go back to my notes here just so that you know where to find all that stuff. They're all under assembly language programming. And the jump instructions are here, and it has been here for a while. Okay, they have been here for a while. When you are looking at subtract and compare, those are here and also here. Okay. Are there any questions? No questions? Okay, so when you read the notes on jump instructions, it will give you basically the same thing that I will be talking about today, but I'm not going to refer to my own notes here, okay? But you know where to find the notes in case you want to refer to it, okay? All right, so we'll start with the simplest jump instruction, which is a unconditional branch instruction, which is basically a go-to. So let's take a look at the jump instruction. And just like before, we start with a real simple program here. Okay. And well, I'm not going to make it like super, easy. So I'll use something that looks like this. Okay. So I have underscore start defining a label, and that label is the address of the no op instruction, because the label is always the address of what is following the label and not the one before. So no op has the address of underscore start, or I should say the underscore start label is corresponding to the address of the no op instruction. Jump is the same thing as a go-to in almost any programming language. It simply means continue execution at where you specify. And where am I specifying?
Start.
Underscore start, which is the no op instruction. So this is unconditional, which means it is going to continue execution at underscore start without asking any questions.
So we'll like create an infinite loop kind of.
It's an infinite loop, exactly. Okay, but this infinite loop will alternate between the no op instruction and the jump instruction, because it has to operate. It has to execute the no op instruction first and then the jump. Yep, go ahead.
No instruction is not the same thing as end of the program.
No, and no op instruction is just basically the same thing as opcode 0 in the toy architecture that we talked about. It's basically the same thing as just the fetch part of the microcode without any actually useful code corresponding to it. So it does increment the program counter to the next one, but it doesn't do anything useful after that. Is that okay? All right. So no op is really here just to show you that we have a loop, but if I want to make this loop as tight as possible, I can take out the no op instruction, so I would just be running the jump instruction, over and over again. Okay. Do you guys want to see this program run?
Sure. Run.
Really? Really? Oh, it's going to run in a really, really tight circle. All right, fine. We'll run it.
Let's call this one dog chasing tail.
Yep, that's pretty much what it is. Okay, so GDB jump, put a breakpoint. Well, let's run this program without any breakpoints. Okay, so we do an R here, and I have a CPU indicator here. You can see one of the core is at 100% all the time. So that's because it's a tight loop, and the processor is just running this particular tight loop. So the question is, what if your program is doing this? And I can guarantee at least half of this class will at least at some point, at some stage, have a program that does not exit. Control C, okay? Control C in GDB will pause the execution. It doesn't stop it. You don't want it to basically stop the program and get out. You want to stop, you want to pause the execution, but without getting out of the program altogether, because this tells you that line 4, the no op instruction, is a part of the tight loop, which is what you need in order to debug your program. Okay? Because at this point, I can do all sorts of stuff. I can say, hey, give me the label underscore start. Okay, you print it. Tell me what is in EAX. Okay, so you can do all sorts of stuff, at this point to help you understand why the program is now in a tight loop. Or if you suspect that you are not understanding the flags correctly, and that's why it's not branching correctly, you can now say IRE flags and say, oh, okay, none of the flag is set. Okay, well, are you expecting that? Okay. Well, I mean, in a real program, this program obviously does not change the flags whatsoever. Are there any questions about what we have talked about so far? Any questions about the jump instruction? You just tell it where to continue execution, and it does not ask any question. It just simply goes and continue execution where you specify. So we need one more type of instruction to get your program going, okay, which is a conditional branch instruction. And that's the only way you can implement any type of control structure in assembly language programming. In assembly language programming, there's no if, there's no for, there are no while, there are no do's, and certainly no switches. No continue, no break, okay? So what we have instead is a whole bunch of conditional branch instructions, okay? So if I go back to my notes here, the conditional branch instructions is kind of a long slide, more or less, and you can probably look at these ones here, and they should look somewhat familiar, okay? We'll just focus on one. In fact, what we'll do is we'll write a program and we'll take a look, and you tell me what it's going to do, okay? So we'll go ahead and write the program, and I'll say JZ, okay, because that's what it's going to use. Okay. So we'll say maybe JNZ. Okay. All right. So we have .text, .global underscore start, typical beginning of any program here, underscore start. And with this program, I'm going to move byte, okay? Now with the program that you are going to write, the width of the operations is going to be important. In other words, you kind of have to decide, am I adding one to a 32-bit register, or am I adding one to a 8-bit register? Am I comparing a byte, or am I comparing 4 bytes at the same time? Okay, because if you get the width wrong, the program will not work correctly. So you kind of have to think about, in each and every single instruction, what is the width of the operation? Is it a byte? Is it a word, 16-bit wide? Or is it a long, which is 32-bit wide? You've got to think about all of those things, and not just take the default, which is long. Okay, so what I'm going to do here is I will put a 0 into register EAL, okay, because it has to be an 8-bit register. And I'm going to say add byte, $1 to AL. And then I'll say J and Z, jump if not 0, okay, to label underscore start, and then no op here. And I would even comment here and say continue execution at underscore start if and only if Z is clear. Okay? All right. So what do you think this program is going to do?
No, just one.
Oh, because when we go back to start,
Finish
you still have to
one.
run that command again. So
It's
we
not
put
penny.
0 back in AL.
It's
add
a root.
1 to it again. The Z flag is then set back to 0.
Let's think about it, okay? Let's think about the first iteration. In the first, this is going to be an infinite loop the way it is right now, because I'm reloading the register to 0 all the time. What if I'm going to change this program to something like this? What about this program?
One's not 0.
So I initialize AL only once, okay, and and then I say add byte $1 to AL. I'm just adding 1 to AL, and then I say jump if the result of the add is non-zero, back to L1. So what about the behavior of this program?
Well, 1, 1. And then the next time you run back, you add 1 to it. It's not 0 still.
And until.
Each time you keep incrementing.
But
then you gotta max out to 8 bytes. So once you get to like 255.
It's 8 bits, so it will get to 255, and what happens when you add 1 to 255?
And then you kick out.
Yep,
Out, yeah.
exactly. So it does get out after 256 iterations.
Yeah.
Yep.
Like once it hits the 256, will it set the carrier overflow flag, or
It will set the Z and the carry flag at the same time, because when you add 1 to FF, all ones, then it will turn back to 0, but at the same time the carry flag will be set to 1. Okay. Well, let's check it out. Yep, go ahead.
How about that 0 flag?
The 0 flag?
Yeah, I thought it turned from like
the zero flag, as long as the zero flag is cleared, it will go back to L1. So it will not go back to L1 and just continue with whatever instruction is next to it when the zero flag is set. That's a good question. So with all of these conditional branch instructions, if the condition that I specify, in this case not 0, if the condition is false, it will not continue execution at the label, and instead it will just go to the next instruction, which in this case is the no op instruction. Okay, that's a good question. Yep.
Are the conditional statements in higher level languages, when those languages are compiled and stuff, is it actually some kind of combination of these?
Oh yeah. Yep, exactly. Everything boils down to this kind of instruction. Not exactly this one, because we have, there are two versions, like one to look for the flag being a 1, one to look for the flag being cleared, and we have one pair for each flag. So we have at least 8 instructions right there. All right, so are there any questions about this particular program? Let's go ahead and check it out, okay? So I'll just go ahead and check out this program. I'll set a breakpoint at _start. I'll set up another breakpoint at the no op instruction. Go through a few iterations just to see that it's adding 1 to register AL for each iteration, and then we'll actually also change the value of AL, because I don't want to have to single step 256 iterations. Well, I suppose I can do that, because I can say 256 and S to step it 256 times, but it's still a hassle to do that. So we'll go ahead and do something about this. So we'll assemble the program, jnz.o, jnz, yes, ld-o, jnz, jnz.o, gdb, jnz.
When you're in GDB, I know it has a capability to set like watch points, which in Visual Studio basically like has a window, and while a loop runs, the value will increment.
Right.
So I've tried using it there. I don't know how it works. Would you be able to?
I have not used that before, so I can look it up and try to figure out how to make it work. So watch
Point.
Okay, a watch point stops execution of your program whenever the value of an expression changes. Okay, so that means if the value does not change, it's not going to stop.
Okay. So this one, it would basically be like a breakpoint if we set a watch point to. Well, we don't have.
Right.
No label.
If you.
There's no label in the symbol table because L1 is not in the symbol table.
But I think the expression can be a register.
Oh, okay.
So with this one, you can say watch $AL. Okay, so I'm suspecting that will work. Okay, so let's check it out. No, that's because we're not running the program yet. It doesn't understand it yet. Okay, so we'll go ahead and run the program. I set a breakpoint at _start already. And now we'll go back and set the watch point. Okay, so now we have a watch point, which is basically saying if any instruction is changing AL, it will stop. Okay, but it will stop after the change and not before the pending change. Okay, at least that's my understanding. Okay, so let's go ahead and continue execution. So single step, we are just going to single step this instruction, which is hardly exciting. So we'll single step, print $AL, it is a 0, continue execution at full speed, and it stops, okay? And it stops because the value of AL just changed from 0 to a 1. Yeah, so it's really nice because it tells you how it is changed. It was 0 and now it is 1, okay? So that's a great feature for debugging programs, especially pointers, okay? If you suspect something is changing a pointer to point to La La Land in C and C++, just watch that pointer, right? Okay, so that's a pretty cool feature. And you can watch any expression also. You can just give it any expression. If the value of the expression changes, then it stops. So you're not just watching a variable, can be any expression. All right, that's good, that's cool. All right, so continue execution, really boring.
Yeah.
Boring. Okay, so at this point I have 250 more continues to go before something actually exciting is going to happen. So I'm going to be conservative and say 249. Continue. Oh, it doesn't look like that. Help C.
Couldn't you
Oh,
just set
continue
AL?
and then a count. Okay, fine. Because VI likes to specify the count before the command, and this one is the other way around. That's fine. Not a problem. All right. Hold on a second here. Why is it -3? Well, that's because by default, when you print a register, the default interpretation is signed decimal. Okay. So that's why it is going to -3, which is basically all ones except for the last one is 101. Okay, the last 3 digits is 101. -2 is 110, the last 3 digits. And then the next one up is going to be -1, and then we're back to 0. Okay, so single step. Now it goes from -2, which is 1111, 1110 to 1111, 1111. So if I single step one more time to add it, it will go from -1 to 0. Now we want to manually check the flags first. Okay, so we want to say IRE flags to confirm that the Z flag is now set, right? You guys can all see ZF here. So that means the 0 flag is now set. Now since the 0 flag is now set and I am specifying a J and Z instruction, should I go back to _start? No.
Finish.
So I will continue to the no op instruction, and I'm all done. Are we doing okay so far with this? Well, you have all the tools already. In other words, I just airdrop you into a forest area. You have a few sticks in your hand, a string, and a flint, okay, a piece of flint. And I'm just telling you guys, happy hunting. Except you're not hunting bunnies in this case, you have wild boars and other dangerous game. Yep, go ahead.
When we have a program, we have a name for our programs, and does that name for our program when we implement it, when we run it, does it get stored in memory somewhere?
The name of the program itself?
Yeah.
Yes, it does. Okay, it is part of the what we call environment variables. So the name of the executable is actually the first thing. If you supply any additional arguments or switches, it will also be represented when you start the program. In C and C++, it will be the arguments of main. So the first argument of main is actually argc, which is the argument count, and then the second argument is a const char pointer argv, which is an array of character pointers. In assembly programming, I'm not quite sure how to get to those environmental variables. We don't really need those for the program that we are writing.
Oh, we don't.
So we don't. Yeah. But it'll be cool to know. I can find out and share it with the class. But for this program, we don't need to know that. Okay, so are there any questions about the conditional branch instruction? So you have the opposite of J and Z is JZ, which means I will only perform the branch to the designated label if and only if the Z flag is set. Okay, this one branches when it is not set. So you have JC, JNC, JO, JNO, JS, JNS. So those are the 4 pairs of conditional branch instructions that forms the basis of the other ones. Okay. We also have JL and JNL. Remember, the L flag is imaginary, it's not really there. It is the exclusive OR of the overflow and the sign flag. It is indicating less than in signed interpretation. You don't need that for this assignment. You don't need it for this particular homework assignment. For this homework assignment, I would say JZ, JNZ, jump, the unconditional branch is going to be useful. And maybe I think JZ is actually going to be, it'll be useful. Okay, that's all you need. All right. So are there any questions? So the next thing I'm going to do, see, we have plenty of time. We still have more than half an hour. But if you think of any questions related to the homework assignment, don't hesitate to ask, okay? Because the whole idea of giving you the homework first and then talk about the concept is to make you kind of think about all of the tools that we have talked about, and you kind of have to think about, okay, but how are these tools related to the homework assignment? We can add, okay? We can increment things, we can subtract, we can compare, okay? So how do we put all of these things together?
How are we going to traverse the field?
The memory space?
Yeah.
Well, you have the add instruction, you have indirect operands. So you have a way to increment a pointer, and you have a way to dereference a pointer. And then, so that will help you compare what you're looking for with the content of whatever the pointer is pointing at. If it does not match, add one to the pointer. Look at the next location. Is that making any sense? Okay. All right. So what I will do is I'm going to give you some examples, okay, just to illustrate. First of all, how do you test your program? Okay, because remember, dot fill is initializing all 256 locations with zeros, which is not going to be helpful if you're looking for bunny, because bunny is not there. Okay, so you gotta be able to load bunny into that space in order to test the program, right? So what we'll do is I'm going to write a text file here. I'll just call it bunny1.txt, and just a whole bunch of gibberish here, bunny, and then a whole bunch of gibberish after that. Okay, so bunny is definitely here, B-U-N-N-Y, all lowercase. Exit the file, and then I'll write another program. I'll just say it's man.s, because the whole point of this program is just to illustrate how do you inject the content of a text file into the memory space of your program. Okay, so we'll just go ahead and specify L1 dot fill 256, same kind of construct as your program. Then we have underscore start, and this program does not even need to do anything. Just a single no op is fine, okay? Because I just need to be able to start the program, stop at the breakpoint, and be able to initialize the content at L1 to the content of a file. That's all we need to do.
I'm just saying you can do that at runtime?
Yep, we can do it at runtime. So we'll go ahead and do the usual thing to gstabs mem.o, mem.s, link the program to mem.o, gdb mem, put a breakpoint at underscore start, run the program. It now stops at the no op instruction. And if I remember correctly, the instruction is called load. So it says it will dynamically load file into the running program and record its symbol for access at GDB. A load offset may also be given. That may not be what I want to do. I figured this out once, and I will figure it out again. Okay, aliases, no. Breakpoint, no. Examine data, probably no. Files, maybe. Internals, no. Obscure, no. Stack, no. Used to be fine. Okay, so we'll go ahead and check files first. Add symbol file, CD, core file, directory, edit, exec, file, no. Forward search, list, load.
It seems like that's what you want though. You want that.
I'm pretty sure I found it before, so just have to find it again. Nope, that's not it. Let's see. Let's try data. Okay. Dump, display, explore, find, output, set. I know I can use set to do it, but it's going to be cumbersome to use just set. Set breakpoint, set check, set debug, disassemble.
When you use set, does it have to be an expression that evaluates to an integer, or just?
You have to say set and then what equals to.
Yeah, that's what I'm saying. So like right there, we're trying to have L1 equal something. Could we say set equals and then a string? And it'll put that
Change the
string
type.
in.
No, you cannot
Change
use
the
strings
type.
here.
Okay.
Yeah, so that's why you have to put the content in the file first. Yeah. Okay, set mode. Nope. Target. Nope. Okay. That's not either.
Running the program. Here.
I have a suspicion it's load. Dynamically load file into the running program and record its symbols for access from GDB. A load offset may also be given.
Why don't you need help on those?
But I have to be able to specify the offset. So. Nope, that's not it. All right, let's try it one more time. Okay, it's just a folder to set. There's a set mem, but that is just changing region settings. It's not for loading content from the file. All right, another cheat. Just Google it. GDB load content, load file. Okay. GDB. I will figure this out and give you guys the instruction to do it. At this point, I cannot remember exactly how to do it.
Try restore.
Restore?
Yeah.
Okay. So let's go ahead and try restore. Okay, restore the content of file into target memory. Okay, there we go. Arguments are file, offset, start, end, where all except file are optional. So we have to specify offset will be added to the base address of the file, and the default is 0. If start and end are given only the file content within that range, file relative will be restored to target memory. All right, so let's go ahead and say restore bunny1.txt, and the offset is 0, and then we want to load it into location L1. It's not a recognized file format.
Call bunny.txt?
I will figure it out and let you guys know. Okay? All right. There's always a way to do it. You know, you can hard code it, but this is like kind of cumbersome, but you can do it. So I'll, yep.
Specify the file name, then binary.
Binary. Like that?
Yeah.
To that one. Restoring file bunny.txt into memory 0 to 2A. That's probably the size. Restore memory write error. Okay, so that means we should just do that. All right. gdb restore okay, dump is the opposite of what we want to do. So we want restore file name binary, and then we have a bias, a start, and an end. If bias is non-zero, its value will be added to the address contained in the file. So it's expecting the file itself to have an address, which in this case it does not. Binary file always start at address 0. The start or end are non-zero. Then only if they're non-zero, then only data between the offset start and file will be restored. These relative offsets are relative to the address in the file before the bias argument is applied. So I want the bias to be L1.
Wait, but so does that optional binary, is it expecting a binary file? Is it expecting a binary file?
It simply means the file itself has no indication what should go where.
Okay.
So it's just a
It's just a
flat
bunch
thing.
of, yeah.
I'll figure out how to get this done. Okay, but if in case I cannot figure this one out, there's an alternative. The alternative is to use the set command, and you basically just say SetBar, or I think SetBar. Okay, SetBar, evaluate expression and assign result to variable var. Okay, so we don't want to use a var here. And you can use a print if you want to. That's one way to do it. So what we'll do is we'll just say L1 plus, give it an offset. Okay, L1 plus 56 is going to get. I think you might need to convince it this is a child pointer first. So we can do a B here. Oops. Cannot access memory at location bound.
Are you running it?
I think I am. Okay, IR. Yep, I'm running. Let's find out. Okay, it's complaining cannot access memory at address.
Oh, 38. You're saying that in memory, you're going at location 38 and trying to access it. Which
There we go. No, it's misinterpreting what is L1. That's what it is. Okay, so you have to take the address of L1, add the offset, and then make it B. And then the next location, which is 57, is going to be U. And N. Yeah, this is going to be tedious.
So I guess that explains the issue that you were having
You can write a
before
script
with.
Sorry?
I guess that explains the issue with the restore, since you were doing L1 and it didn't see it as.
Oh, ampersand L1?
Yeah.
Okay, that makes sense. Okay, but if all fails, this works. All right, I have just put bunny into the memory content by initializing the content 1 byte at a time. Okay, so what we'll do is we want to confirm that, right? So let's go ahead and confirm it. So x/256 BC, okay, because I want to print them out as characters if possible, and starting at L1. This is odd. It's still, it wants me to use an ampersand, and you can see bunny is here, B-U-N-N-Y is here, and it is starting at location 80. But if you compare that to start, which is L1, which is 75, 80 minus 75 is basically 56. So there's one way to, this is one way to inject it. And let me check the other approach first. Okay, so let's go back and check restore. And it wants the address of L1. Yep, that works. Cool. Now if we dump out the content, now we have the junk here, and then we have
Bunny should be a 12.
Yep. Well, bunny is in here somewhere,
Yeah,
right?
yeah, we see that.
It's right there. All right, so very good. So we figure out how to load any content into memory to test your program. Right. So now we have all the tools. So I gave you a few stakes, a few pieces of flint, a string, another stake, And this time I even give you a decoy.
Let's do that.
All right. So I'll give you some example program. How do I initialize a chunk of memory to, say, all FFs? Okay. So this is what I'll do next, and this is going to be important because your program is going to have, I would say, at least similar features. Okay. It won't be exactly the same, but it will be similar. So we'll go ahead and say init mem. This is my new program. Dot data L1 dot fill 256 and dot text dot global underscore start. So this time I start off with all zeros at the 256 bytes at L1. I want to change them. Okay, I want to change all of those locations to FFs, or all ones in binary. So I need some kind of a loop to do it, right? But we already talked about some kind of a loop. And since you don't need to write this code in the most optimal way, so there's a variety of way of doing it. You can keep track of a pointer in addition to a counter. Okay, so you can use two things to do it. Or you can just keep track of a pointer and indicate where the pointer is supposed to stop. Okay, when you get to this location, it's time to stop and don't continue any further. Okay. So I'll just go ahead and use that approach. So the first thing I want to do is to move L, and you guys can fix my error, by the way. L1 into EAX, okay. This is the initialization. And then in the loop here, I will use L2 as the beginning of the loop. In the loop, I'm going to move a byte 0xFF into wherever EAX points to. I will increment a EAX by 1. So you can fix my error if you want to. And I will say, let's compare that address to the end address. If it's still before the end address, I want to go back to the beginning. If not, I'm ready to exit the loop. So what I want to do is I want to compare EAX to the end address. Now, since I know that I have 256 bytes to initialize, that means L1 plus 256 is the end address. Okay? When the pointer gets to that location, it means I'm all done, right? Is that okay so far? So I'm going to compare L1 plus 256 to register EAX. And yeah, I have a few errors here. Okay, I want you guys to fix it. And I will say J something something to L2, and this is the exit code. All right, fix it. Okay, the intention of line 7 is so that EAX is initialized to point to the first location that I want to initialize to FF. Okay, there's a problem with that instruction.
So copying the content at L1, not the address of L1?
Exactly, that is, so the way it is right now on line 7, L1 is a direct operand, which means it goes to the location at label L1, grab 4 bytes from that location, and put those 4 bytes into EAX, which means I'm guaranteed to have all zeros in EAX because .fill initializes those locations to all zeros. Okay, so how do I fix it?
Put it as a immediate operand.
We want immediate, right? We don't want a direct operand, we want an immediate operand. So that's the way we fix line 7. Okay, so let's fix this one. Oops, wrong place for the $. Okay, there we go. All right, so we move on to L2. That's okay as a label definition, not a problem. We look at line 10. Do we have a problem at line 10? Are we moving the parent into parentheses EAX, or do I not need the parentheses? Which one do I need? I need the parentheses because I'm treating EAX as a pointer, and I'm dereferencing and say, oh, don't put FF into EAX. Put FF into where EAX points to. That's what it is specifying here. And that's okay. That's what I intend to do. Okay. Moving on to the next instruction, which is on line 11. Okay. I'm trying to increment the pointer. Okay. I'm done initializing that location already. Let's move on to the next one. do we have a problem here? Move? Why do I want to copy and overwrite register A? I want to add, right? Okay, so let's fix that one first. All right, so let's add. Okay. So is that good? I'm adding immediate one to register AL. Now this is a very common issue because this code will work for a short while. Because it will, as long as we are not having a carry from bit 7 to bit 8, this will do the same thing as add long. Go ahead, sorry. Okay, so this will do about the same thing. Go ahead.
Well, like, isn't the AL only specifying half of EAX?
Not half, a quarter. Only a quarter. This is the least part of EAX. But the problem is this code will work as long as we don't have a carry from bit 7 to bit 8.
As long as we stay in the range.
Exactly, but we don't know how long we can stay within that range because the starting point of L1 can change. It can vary, you know, from one compiler to another compiler. Okay, from one assembler to the next, it can change. So this instruction is really dangerous because it will work for when Bunny is not, or when you're initializing the first portion, but then it will stop working after a while.
So do we want to add a full word?
Yes.
Or a quarter?
A long.
That's long, yeah.
Yeah, so we want to change this to a long, which means we cannot use AL. We have to use the entire register. Okay? And this one is a nasty one, you know, line 11, before I fix it, is a nasty problem because it will work for a short chunk of memory, but after you get past, like, you know, whatever number of bytes, in order for bit 7 to have a carry to bit 8, then it doesn't work. Okay? In fact, it will flip back to an earlier location where, you know, you're not even supposed to touch. Okay? So you have to kind of understand why this instruction was not working, was not supposed to work. But the reality is it does work for a short while. That is the biggest problem.
One of the logic error kind of things.
It's not it's not exactly a logic error. It's not making the wrong decision, but it is using not enough parts. It's using a part of EAX when it should be using the entire EAX. So because EAX is a 32-bit register, right? It's a 32-bit register, and let's say these are byte boundaries, okay? If I'm adding to AL, I'm only affecting the least significant A bits of EAX. In other words, if this goes to FF, okay, and I'm only doing an add byte to EAX, to AL, it will turn these two to 0, 0, just like an add long will. However, an add long will also change the least significant bit of this byte here. But add byte is not going to change it. Is that making any sense? Okay, all right. All right, so let's take a look at the instruction on line 12. Okay, that looks okay to me. I am comparing the pointer, not what the pointer points to L1 plus 256, which is 1 byte past the last location that I need to initialize, which is okay because the add one is right before that, so that's why I have to compare to the location after the last location. So now the question is, what am I going to use in place of the question marks? Okay. Remember, when you have a compare long instruction, you are subtracting the first operand from the second operand. Okay. With this one, it's actually pretty easy because we are only single stepping every single byte. So a few instructions will work in this case. What do you think? So normally EAX is less than the end address, right? But that's using the unsigned interpretation. Unsigned interpretation. So when you are subtracting a larger quantity from a smaller quantity using the unsigned interpretation, which flag would turn on? The carry flag, the borrow flag, right? So normally the borrow flag should be on, which means EAX is less than L1 plus 256, and that should get me back to label L2. Okay, so JB or JC will work in this case. This will work. But I can also change the JC to JNZ. That will work as well.
Yeah.
It means, when if I have not reached the destination address, go back and do it again. Okay, so in this case, JC will work, JNZ will work as well.
Could you also look at the sign flag, if the sign flag is set? If you're subtracting a larger value, a smaller value.
Yeah, you can look at the sign flag too, because if I'm subtracting a larger quantity from a smaller quantity, the sign flag will be set normal, because it will be representing a negative value. But that will only allow you to specify a range of initialization of 2 gigabytes. Because if you get past 2 gigabytes, then the sign flag cannot reliably tell you about the result of the comparison. But in this case, yes, because we only have 256 bytes. So that solution will work, but has a limitation.
I see.
Yeah. But JB or JC and JNZ are both proper solutions in this case. All right, so let's go ahead and run this program, and we'll do a AS G steps J-O init mem.o init mem.s ld-o init mem.o. Oh, I forgot to specify the start label. And you can see it was only a warning because the compiler or the assembler is making an assumption and say, I'll just take the first thing in .text as the entry point of the program, which in this case is okay, but in general it's not okay. So it's much better if I just specify the start label here. So let's go ahead and redo the assembler and redo the anchor. There we go. GDB and then put a label at _start, okay, run the program. And just to spice things up a little bit, I'm going to redo the restore thing, okay? So we'll restore bunny1.txt as a binary file into where L2 is. L1, sorry. If I put it into L2, that would be a big problem because I'll be overwriting the program. Yeah, that would not be a good idea. Okay, so if I look at the 256 bytes starting at L1, then it will see the junk stuff in the file followed by all zeros, which is what you would expect, right? Okay, so now it's time to actually run the program. Single step, single step, single step, single step, single step. Now you can see how the program just went back to label L2, okay? Because when you look at the line numbers, it went from 11 to 12, 12 to 13, 13 to 14, and then the JC, which is a conditional branch, because it says branch to L2 if and only if the carry flag is set. And it does go back because the carry flag is set, okay? So it will keep doing this until the carry flag is cleared after the add instruction, then it will stop, right? So what I'll do is I'm gonna test it and see if it is smart enough to watch for this condition, okay? If I just say watch EAX, it'll be super boring because every time I change EAX, it will stop. And most of those times is not exactly interesting, right? So what we'll do is we'll say, hey, I want to check the condition of EAX being the same as L1 plus 256. Okay?
So it should basically like what GDB is doing.
Because it will be false all the time, except for the last iteration, then we turn true, right? I'm pretty sure it will complain about types and whatnot. I'll let it complain and then we'll fix it. Nope, it does not complain.
Wait, so could you right now print? It has no value.
Well, EAX is just an integer, right? So if I print the other one, which is L1 plus 256, yep, well, I'm suspecting it will do the right thing.
Let's find out.
Let's find out. Continue execution. Go at full speed. Now, give me a segmentation fault.
If you look where you printed it, L1 plus 256 is actually bigger than EAX.
Say again?
Yeah. It's like the last four, like 17.
Okay, it has lost track already. So it didn't stop. You know, the breakpoint, the watch point did not stop. And it went past the no-op instruction, and that's why the program kind of crashed because of that. All right, fine. We'll put a breakpoint on line 17 and run the program from the starting point again. Oh, I forgot one thing. I did not reinitialize the memory. Let's check the memory first and see if it, well, if I rerun the program, I think it's reloading everything, so everything should be back to normal. Let's check. Yeah, everything's back to normal because every time you rerun the program, it will reinitialize everything. So if it's a dot, so the dot field will automatically reload all the zeros into L1, and that's why it's all reinitialized. So we'll go ahead and just continue execution because this time there is a no-op instruction where the breakpoint is, and it does stop there. Okay, because last time it did not. I was assuming the watch would work. It did not, and that's why we just ran past it and did not stop. Okay, so now we want to take a look at L1, 256 bytes at that location, and they're all -1s. What? -1? Didn't we put FF into those locations?
Step sign, so FF.
Exactly. Yep. So if I change the print, the X command to use BX, which is printed in hexadecimal, then it will be all BFFs. So it does work. Okay, but I'm not ready to give up the watch.
Well, I was going to say, you can set up arbitrary variables inside of GDB, right?
Say again?
You can set up like arbitrary variables in GDB. So if you just set a variable to that value.
I don't think so. I don't think you can set up a variable, but you can watch an expression. So I think what's happening is it wants to check the type to. Okay, I'll try this. Okay, we'll be comparing EAX as a char pointer to the address of L1 as a char pointer plus 256. And I'll even give it extra parentheses just to be sure. Right? Now there can be no confusion. Okay. And in addition to this, I will print it just to evaluate it is true. Right? Okay, let's go ahead and start the program all over again. Redo the print here. It is false, okay, which is fine. Okay, that's the way it's supposed to be. And just continue execution. And this time it stops. Okay, so it's the type casting that is causing the issue. Yep, it's the type casting that's causing the issue. If I force everything to be a char pointer, then everything is good. So now, it is right at the point where EAX, in the previous iteration, it is the byte location before, and now it is at the location where we want it. So when we single step, everything should be okay. So the compare, if I print EAX at this point in hexadecimal, and print L1, they are the same. Yep. So watch is cool if you know how to do it.
But they're not the same.
Yeah.
They're not the same.
They're not the same?
187 and 0.
1 and 0.
Oh, L1 plus 256, sorry.
Plus.
That's the end location. We want the end location. No,
489.
no. That's the problem because L1 is misunderstood as the address of an int. That's why it doesn't work. So that means we have to cast it to a char pointer first. Nitpicking GDB. Okay. So when we single step, The JC should not go back because now they are the same. There's no carry anymore, no borrow anymore, and so we fall through to the no out instruction. Yep. All right. So are you guys getting some general idea of what to do with this one? You have to do similar thing to scan through the memory. Okay, the first thing is to learn how to do the restore, okay? Because you have to put a text file content into where L1 is so they can test whether bunny is there or not, okay? So that's the first thing you do. The second thing you have to do is to scan through that memory region to look for the pattern. Now, I would work on this program in stages, okay? So in the first stage is simply to scan through the whole memory content for a single byte value. Don't look for anything fancy, just look for lowercase x, okay? And then make a test file like my buddy1.txt where you have one single x somewhere in that file, just one, okay? And see if your program can find that one single x or not, okay? Once your program can do that, then make it look for 4 characters at a time. Because you can kind of doctor compare long to look for 4 characters at the same time. Okay? So I would do that. So look for bunn bun instead of bunny. Okay? Once you can locate bun, you just have to say, okay, I have just found bunn. What about the last one? Okay? Move the pointer to the last one. There's a little trick to do that because you have to skip 4 bytes instead of 1 to look for the Y. And then if you also confirm that it is a Y after bunn, then you found it. Otherwise, you did not find it, and you have to remember to restore the pointer and go back to the beginning to continue the search. Are we kind of doing okay so far with the concepts?
What kind of value are we doing to store it to that 256? What kind of value are we going to store it there?
It's up to you to make your test cases.
So, I mean, for the homework, what kind of value do we have to store there? It's
something that has bunny in it.
Anything as long as I have a bunny.
Yep.
Anything, I can put anything there.
Well, or something that does not have bunny, because as one of the conditions, you have to detect that you have scanned through all 256 bytes and cannot find bunny. In that case, you have to initialize EBX to 0 when you get to check here.
So our conditions, one condition is we can't find anything, have to be 0, and a lot of conditions we have to have something.
Okay, we're going to go to the lab, so
yeah.
When we get to the lab, it'll read the instruction in the homework assignment and see if you have any questions about the description first.
Sure. I read it.
Right.